So, as a subject, as introduction to my lecture, I chosen the Banach-Tarski paradox. Indeed, it's a very counterintuitive result, which states that in one of simplest form, that one can consider unit ball in three-dimensional space, count it into finitely many pieces, and then using rotations, reassemble them to get two copies of the initial ball. This result was obtained by Stefan Banach and Alfred Tarski. On the first slide, you can see the title taken from the original paper. The paper was written in French, and it's yet another reason to present it as an introduction to this chair Lamé. So there are several ways to present this lecture. The one I've chosen here is actually by putting the titles of the main papers. So we start with the paper by Banach and Tarski from 1924. We will explain this result, namely this paradoxical decomposition of the unit ball, and then we'll talk about notions concerning groups. We'll see that actually behind this result are the groups. And the notions are amenability, which was introduced by von Neumann in the paper a few years later. His paper was written in German, so Allgemeine Theorie des Masses, and actually was published in the same journal as the Banach-Tarski result. It's a Polish journal. And then we'll talk about property T. Property T was introduced by Kazhdan in 1967, and his paper was written in Russian. Also, concerning property T, we'll be interested in many spectacular applications. The one I would like to single out here is the one due to Margulis, and it makes a connection between this property and some problems in combinatorics and computer science. So this was chronological presentation of notions that are that will be crucial in my class. As a presentation of this lecture, one can also look at from the linguistic point of view. So I will present the result, the mathematics behind these results in English. When I'll talk about the, say, historic or cultural context of this result, because there are diplomas from French embassy in Moscow, from French consulate in St. Petersburg, il y a Monsieur le Consul. So I'll do it in French, and maybe when we'll talk about developments, about these notions related to Banach-Tarski paradox, I'll switch to Russian. So the way we'll present the result is actually already simplifying it a little bit. Instead of talking about the ball, we'll talk about the sphere. But once you understand how one does it for a ball, it will be very easy to obtain an analogous result for the sphere. So the result states that S2 sphere in R3 can be decomposed into 8 subsets. First 4 we'll call A's, and the remaining ones by B's. So S2 is a disjoint union of these 8 subsets, and one can find the rotations so that if one considers the first 4 pieces using rotations, one can obtain another copy of S2, and using other rotations for B parts, one can obtain the second copy of the original sphere. It's a very famous result. There are books just about this theorem. Also, I remember reading the autobiography by Feynman. He says that when he was hesitating between studying mathematics and physics, actually this result was presented as something that mathematicians can do, and I'm afraid still cannot do, right? So I'm afraid you cannot achieve what you asked for. Okay.
Not in the real world.
Not in the real world. Not in the real world. Right.
Maybe someday.
Right. So that's somehow the advantage of mathematics over the real world. Behind this result, there is a group theory. There is a group, namely a free group. Free group of rank 2. Elements of this group are the words one can write using the letters A, B, and the inverses. And we suppose that we consider the words which are fully irreducible, so that you cannot have a letter and its inverse after it. And the trivial element corresponds to an empty word. And the multiplication is by writing one word after another, and doing cancellation, namely whenever you see the letter and its inverse, they will cancel. Then one can consider the following subsets to obtain already this paradox in the case of the group F2. The subset A plus will consist of words which start with the letter A minus. This will be words starting with A inverse. And in similar way, we defined B plus and B minus. So any element in this group F2 is represented either by a word in A plus, A minus, or A B plus, B minus, or it's an empty word corresponding to identity. Now, if we consider, if we multiply all elements in the subset A plus by A inverse, okay, so we multiply the words starting with A by A inverse, so this A will be cancelled by A inverse. So in this way, we'll obtain all words except the one starting with A inverse, because we suppose that we consider three irreducible words. So F2 will be sum of the subset A minus and the subset A plus translated by A inverse. And similarly, F2 is the union of B minus and B plus translated by B inverse. So indeed we obtain a paradoxical decomposition for F2 out of finitely many pieces disjoint subsets of F2, using translations, we obtain 2 copies of the initial group. Okay, and it's a small exercise to actually slightly modify one of the sets to include identity, so that one can decompose F2 into 4 disjoint subsets, and out of them obtain 2 copies of F2. Okay, so we know how to get this paradoxical decomposition for a free group. How do we relate it to the sphere? Namely, it's enough to find among isometries, among rotations of 2-dimensional sphere, 2 rotations which generate a free group F2. And this is easy to do. It's enough to consider one rotation around z-axis and the second one around x-axis with the following rational coefficients. Okay, so the check that this matrices really correspond to rotations is very easy. It's just the Pythagorean identity that 3 square plus 4 square is equal to 5 square. And now, how do you check, how do you prove that it's a free group? That if you write any word with these rotations, which is free irreducible, you don't put a rotation and its inverse, it will, if the word is non-empty, it will represent a non-trivial rotation. Well, we can reduce to the situation when actually we start with the word starts with rotation phi, and then if you consider a word starting with phi of length k, it's immediate to see that if you apply this rotation to the vector 1, 0, 0, you obtain the point with the coordinates a, b, c divided by 5 to the power k. K was the length of the word, and a, b, and c are integers. Yeah, it follows immediately from the way these matrices look like. And now, by induction, you prove that this coefficient b is not divisible by 5. In particular, it's a non-trivial. Well, we moved the point 1, 0, 0 to another point, and indeed the word is not non-trivial. Excellent. So we have a free subgroup generated by 2 rotations. So now, if we consider sphere minus the points which are fixed by rotations, okay? So let G be the group generated by these 2 rotations, and let D be the set of all fixed points fixed by some non-trivial element in this group. So now our group G acts without any fixed point on the set as a sphere minus this countable subset D. So one can induce this paradoxical decomposition from the free group onto this set. Well, this is something that somehow we do very often in mathematics. Here, however, one has to stress that in order to do this, in order to choose the representative of each orbit for the action on the group on this set, we need the axiom of choice. So indeed, one way of thinking about this result of Banach and Tarski that is showing really very strong counterintuitive consequences of this axiom of choice, and actually it might be considered as a reason not to admit this axiom. So this is a very important point in this proof. Okay, with decomposed sphere minus the small subset, Well, let us finish the proof. Let us decompose the entire sphere S2. Well, in order to do this, we'll find rotation, we'll find the axis rho and the angle theta, such that this rotation, all powers of this rotation applied to the subset D give us disjoint subsets. Okay, this is immediate from the fact, the existence of such a rotation, from the fact that we consider countable, that subset D is countable. Okay, so it follows from work of Cantor, which actually was born on this island, that indeed such an axis exists. And let us call A the union. It's a disjoint union of D under under this rotation and all its non-negative powers, and defined B as S2 minus this subset A. So in this way, S2 is of course the union, disjoint union of these two subsets A and B. Yet if we rotate the subset A, the union of B and A rotated under this rotation gives us S2 minus D. So now S2 can be decomposed into these two pieces. Using rotations, one can obtain from these two pieces S2 minus D. We already know how to obtain from these two copies of S2 minus D, and again, using the same decomposition, we can obtain two copies of S2. So that's it. That's the content. That's the proof of paradoxal decomposition. Voilà ici les auteurs de l'article. À gauche, Andrzej Zuk, à droite, Stefan Banach. Parfois, il n'est pas facile de savoir à quel moment on a pris les photos. À gauche, les photos de Tarski, c'est quelques années avant l'apparition de l'article. Il s'agit de deux mathématiciens remarquables qui ont marqué le XXe siècle. Donc il y a plusieurs livres, plusieurs biographies de Tarski et de Banach. Tarski a contribué au développement de la logique, et surtout en ce qui concerne l'aspect algébrique, la relation entre la logique et la théorie des groupes. Et Banach en ce qui concerne l'analyse fonctionnelle. D'ailleurs, sur la couverture du livre sur Tarski, on voit un tableau peint par un peintre très célèbre, Wittkacy. Ce qui est peut-être déjà très intéressant, ce qu'on pourrait mentionner ici, qu'il s'agit d'une collaboration, et c'était vraiment le début des articles qui étaient écrits par plusieurs personnes. Donc voilà une photo de l'université à Lvov où ils ont travaillé. Il s'agit de l'université qui était créée par le roi Jean Casimir. Donc voilà, c'était un beau bâtiment. On a envie peut-être de travailler ici. Mais en fait, ils n'ont pas travaillé dans les bâtiments universitaires. Ils ont préféré un café. Donc voilà les photos d'un café très célèbre, café écossais. Voilà, où on servait du café, mais pas seulement, comme le nom indique, aussi du whisky. Et je dirais que c'est vraiment, c'est très moderne. C'est comme ça qu'on fait aujourd'hui les mathématiques, pas seulement dans les bâtiments universitaires, mais on aime bien se réunir dans un café et discuter des mathématiques, de démontrer le théorème. Et il est peut-être aussi intéressant que dans ce café, il passait beaucoup d'heures. Il y a un cahier qui s'appelle cahier écossais, où on peut trouver les problèmes qui étaient formulés à... Peut-être je vais agrandir un peu. Qui étaient formulés à ce moment. Donc, à droite, on voit les problèmes formulés par Banach, c'est écrit en polonais, et à gauche, voilà, on peut voir, parfois, à côté d'un problème, il y a aussi un petit prix qui était offert pour la solution. Donc ici, c'est une bière. Voilà. Voilà. Peut-être aussi, donc, ici, on voit la première page de l'article qu'ils ont écrit. Et ce qui est intéressant, peut-être, c'est avoir donc l'article est en français. Et si on regarde les références, on voit, par exemple, Hausdorff, Grundzüge der Mengenlehre, donc la référence à un livre qui est écrit en allemand, à un article écrit par Vitali, qui est en italien, sur le problème de la mesura, et aussi un autre article de Banach, qui est écrit aussi en français. Donc, c'est aussi une période où on écrivait dans plusieurs langues. Aujourd'hui, c'est à cause de ça que j'ai commencé mon exposé en anglais. On écrit surtout en anglais. Et peut-être donc on peut comparer, bon, il faut que Euler soit présent dans cet exposé. Donc on peut, si on regarde les écrits de Euler, donc déjà il n'y a qu'un seul auteur. Donc à l'époque vraiment on considérait que les maths c'était comme les arts, comme la peinture, comme la littérature. Il n'y avait qu'un seul auteur et son œuvre est écrite en français, en latin, bien sûr, en latin. Et donc aujourd'hui, c'est très commun qu'il y a des collaborations, qu'il y a des articles écrits par deux, par trois, par plusieurs mathématiciens. Donc de ce point de vue, c'était très moderne la façon de faire les matematyki. Dwa свойства по теории групп, которые связаны с этим парадоксом Банаха-Тарского, это аминабельность и свойство T. И мы скажем, что группа аминабельная, если существует конечно аддитивная мера на всех подмножествах этой группы, которая инвариантна по сдвигах этой группы. И скажем, что у группы свойства T, если тривиальное представление, это изолированные в пространстве всех представлений, унитарных представлений этой группы. Да? Тогда пишем T в скобках, T тривиальная и изолированная. После работы Lebega было интересно очень знать, если существуют другие меры, чем мера Lebega. Так, например, на сферах, если мы говорим об мерах, которые конечно аддитивные, они определены для всех подмножеств Lebega и тоже инвариантные по изометриях. И так, например, и эта проблема для S1, S2, S3 для всех сфер. И так, например, для S1 существуют другие меры. Почему? Потому что можно думать, что S1 это группа, да? Это группа оборотов, И группа оборотов – это аминабельная группа. Из того мы знаем, что существуют другие меры. И тоже от того вытекает, что для S1, для округа, нет парадокса Банаха-Тарского. Да? А для S2, 3 и дальше нет других мер. И это можно доказать, используя парадокс Банаха-Тарского и тоже группы за свойством Каждана или вариантом этого свойства. Right. And just to finish, I put some survey papers that I wrote, which correspond to the topics of this of the class. So maybe the first remark that one can still write papers in French. So this is a seminar Bourbaki talk about groups generated by automata. In the lectures, we'll talk about also about property T for countable groups. We'll learn how to construct new groups with property T, for instance, among hyperbolic groups. In order to construct new amenable groups, we'll talk about groups generated by automata. And also, we'll talk a lot about connections with problems in probability, combinatorics, and computer science. We'll also mention, we'll talk about analysis and geometry on manifolds. Already in my colloquium talk last week, was introduced the work of Atiyah. Okay, thank you very much.
Кажется, это был первый доклад, на котором я был на 3 языках. Je crois que c'est la première fois que l'exposé est électronique. Question, вопросы, questions. So, thanks again. Да.
First, the concrete question. Is it possible to identify the three properties of spheres in such a way that, and then we can consider intersection of these pieces of pieces A and B type? I mean that we move these pieces of sphere and to the first property, which consists of pieces of type A, and then we consider intersection with the pieces of type B. And if it looks like that, this process doesn't stop, it doesn't stabilize. So you get an infinite splitting of original sphere if we iterate this procedure. And the first question, is it true? And is it true that it is impossible to split the sphere in such pieces that identify the three copies of sphere in such a way that the intersection process will stop?
So you would like to put the pieces inside the other piece to make it smaller and smaller?
Yes, I mean to split the piece by intersection with pieces of another type.
All right. So actually, so what we've seen here, there are, it was a particular way of stating it. Actually, if we talk about this uniqueness of the Lebesgue measure on the sphere, so the first thing to do it as S2 is concerned is to prove that such a measure is absolutely continuous with respect to Lebesgue measure. And the way you do it is actually that if you take arbitrary small piece of this very small, arbitrary small ball around a given point, you can cut the sphere into finitely many pieces and put all these pieces during rotation inside this epsilon neighborhood. Okay? And here epsilon can be arbitrarily small, and from this, as you can easily see, follows that any such measure is absolutely continuous with respect to the Lebesgue measure. Okay, so this set you can make arbitrary small. By the way, I stated this problem for Lebesgue for measures defined on Lebesgue measurable subsets. If instead of the Lebesgue subsets we talk about Borel subset, it's open. Okay, and the point is that when we do this paradoxal decomposition, we're using the subset which are not measurable, of course. However, in order to prove that it's absolutely continuous with Lebesgue measure, you have to consider the subsets of Lebesgue measure 0. And when you intersect them with subset of this which you get in the paradoxal decomposition, they are still measurable. Okay, but you cannot do it in the case of the Lebesgue sets. Okay, if you intersect Lebesgue sets of measure 0 with the subsets, they are not Borel. They are not Borel. Okay, so it's a very so indeed this decomposition you asked for, it's useful in this situation.
You mentioned that S1 is a group space, and that's the reason why this space doesn't have Banach-Tarski paradox. But S3 and S7 are also group spaces. So it's actually...
yeah, so what is important that the group of rotation is commutative. Okay. It's commutative, and well, actually, maybe you suggested the first theorem that will be proven in the class is that, so it's a theorem of Banach, that commutative groups are amenable. Okay, so we will construct for any commutative group, we will construct mean invariant measure defined on all subsets. Okay, which is invariant under translations, finitely additive. So in particular, you can define in this way density for all subsets of integers. And the way we'll do it is using the Hahn-Banach theorem. So maybe it's the most spectacular use of this theorem from function analysis, that indeed you can define density for arbitrary subsets of integers.
Поблагодарим нашего докладчика снова.